Welcome everyone to a video on practicing related rates. We have two objectives for the video. We're going to set up some related rates and we're going to solve some problems using related rates. So I'm not going to lie to you, I'm going to preface this at the beginning. I'm not very good at related rates. I struggled with it when I took calculus in high school. I struggled with it when I took calculus in college, and I'm still not great at it. So I'm going to do my best, and if you have any questions, please let me know. So when we deal with related rates problems, most textbooks are going to tell you to deal with it in 5 steps. The first step is going to be to draw a picture of some kind. The second one is going to be making a list of what you know, what you're trying to know. The third one is going to be setting up some sort of equation, some sort of relationship between what you know, what you don't know, and the situation itself. The fourth one is to differentiate everything, usually with respect to time. So instead of doing derivatives the normal way, you're really treating everything, including x's, with implicit differentiation. And the fifth and final thing is to substitute in what you know and then hopefully solve for the only thing that you don't. So these problems can get a little bit difficult. Some other things to keep in mind is you need to know a lot of geometric formulas. A lot of these deal with geometry, whether it be right triangle stuff, so sine, cosine, tangent, and right triangle trigonometry, in addition to the Pythagorean theorem. It could be area problems, it could be volume problems, it could be surface area problems. You really got to know a lot of your formulas. And we'll talk a little bit about that when we talk about setting up related rates. So, speaking of which, the first thing we're going to do together is we're going to set up some related rates. I have 2 situations here that we're going to set up related rates, and we're not going to solve for anything. We're not going to have an exact final answer, because I took out some of the information that we would have needed for that. Mainly this is to practice with setting up those equations and taking the derivative and seeing what that looks like at that step. So we're not doing the 5th step pretty much, but we're doing everything up until that 5th step. So I got 2 situations for you, and if you haven't done it already, make sure you pause the video to copy them down. And I would love for you to try them out ahead of time and then check what you did against what I did. Maybe we can see where some things might have gone wrong or where we can improve a little bit. Or maybe we just got it all right and we're comfortable and confident. So I'm going to move the first one out of the way for us so that we can talk about that one later. The first thing we're going to talk about is we have a 10-foot ladder that's being leaned against a wall. The ladder begins to slide down the wall at a rate of 2 feet per second. At what rate is the distance from the ladder's base to the wall changing? I think I did give us all the information we really needed for this one, but we're just going to set it up and see what that looks like. So,
first thing I'm going to do is I'm going to draw the wall, I'm going to draw the floor, and then in a different color here we can draw the ladder. So,
we know a few things, right? We know that there's going to be some sort of height of the ladder against the wall. There's the distance from the ladder's base to the wall here, so we can call that maybe the base. And then we know that the ladder itself is 10 feet long. So what pops out at you? What pops out at me is Pythagorean's theorem. We haven't really been talking about angles or anything like that, and we're dealing with a right triangle, so Pythagorean's theorem is what pops out to me. So we are essentially dealing with a squared plus b squared equals c squared. Arguably one of the most common equations that get set up with related rates. Some lists of things that we know, and we are trying to find out. We know that the ladder itself, so the c in this case, is going to be equal to 10 feet. We know that the a is going to be, let's say that the a is h feet. The b in this case would then be, b feet. And we know that the ladder slides down the wall at a rate of 2 feet per second, so that is talking about the change in height. So that would be dh dt, and that would be equal to negative 2 feet per second. It's decreasing at 2 feet per second. So let's rewrite this with some of our information here. We have h feet. No, let's not put the variables on that, actually. Not the variables, let's not put the units on that, my bad. H squared plus b squared is equal to 10 squared. So here's an important distinction. It doesn't tell us at what time any of this is occurring. It doesn't tell us like when the height is 2 feet from the floor or something like that. If they told us exactly when they're wanting the information, we wouldn't plug that in right now. We would just set up this equation. But since the 10 is going to stay 10, like the length of the ladder itself is never changing, it's okay to plug that in now. So now that we have an equation and we've plugged in, we've got it set up where we need it to be, we're going to differentiate it with respect to time. So we're going to implicitly differentiate everything with respect to time. So the derivative of h squared would be 2h dh dt plus, that would be 2b db dt equals the derivative of a constant is 0. So we can solve for dB dt, because that is what it's wanting us to solve for. So we can move this over by subtracting it. So we have 2b dB dt is equal to negative 2h dh dt. And then we can do a little bit of substitution and we can cancel some things out. First thing that I note is the dh dt, this right here, is equal to negative 2 feet per second. Negative 2 times negative 2 is a positive 4, so that would be 4h is equal to 2b dB dt. And then we can divide by 2b, so that would end up with dB dt is equal to 4 divided by 2 would just be 2h over b. So we don't know what this rate is right now. We have it in terms of some variables that we don't currently know. But we could find it out if they gave us that initial information or we had some way of finding it. Right now we don't, so that is as far as we're going to go. All right. The next one. Water is draining from the bottom of a cone-shaped funnel at a constant rate. The height of a funnel is 2 feet and the radius at the top is 1 foot. At what rate is the height of the water in the funnel changing? So this one is a little strange and it caught me off guard. So first thing, we're talking about a cone and we know that water is draining from it, so the volume is draining from it at a constant rate. The volume is decreasing at a constant rate. The volume of a cone or any pyramid is 1/3 times the base area times the height. So 1/3 times big B times h. We can write that in a different way for specifically a cone, because the base area of a cone would be pi r squared. So we would have 1/3 pi r squared h be our formula. And if you're having trouble with volume formulas or anything like that, I'd recommend looking them up. Maybe check back from some of your geometry notes from years back, and that might help you a little bit. So this is the volume formula we're going to use. And if you notice, I haven't drawn a picture yet. So let's go ahead and do that.
We'll draw a nice oval. It's going to look a little ugly, but that's fine. We're not perfect. We don't have to be. And that has water. Oh, I'm still on the straight line tool. Let's fix that. that is going to have some water inside. There we go. So,
what do we really know about this situation? We know that the initial radius of this is 1. And we know that the initial height is 2. I'm going to leave the units off for now. But we don't know what the current radius or the current height is. That information we don't know. We don't know what this is. And we don't know what that is. So it might seem like we don't know a whole lot to start. And that's not entirely untrue.
what we could do is we could take this formula right here, and we could differentiate it implicitly. If you do that, you're going to end up with some weirdness. We're going to have dv dt is equal to, I'm going to leave off the 1/3 pi, and then we can use the product rule with this. So r squared h, the derivative of r squared is 2r dr dt, derivative of h is dh dt, product rule says to multiply and add. So that would be 2rh dr dt plus r squared dh dt.
That is a lot. And that is right. It's not wrong. But we're not really given a whole lot of information about, like, the change in, like, imagine how much information you would really need to know for this. We would need to know what r is at any given moment. We would need to know what h is at any given moment. And we need to know the rate at which the radius is decreasing, the height is decreasing, and the volume is decreasing. There's too much unknown there. So can we take this and maybe make it a little bit nicer before we differentiate it? I'm not sure where this came from. Oh, there it is. So we can actually do that by talking about some relationships. There are more relationships going on than just the volume. They gave us the original radius. Oh, I'm still on the straight line tool. They gave us the original radius was 1, and the original height was 2. So we can actually set up some similar triangles here. We're really going back to geometry. So I'm going to take a cross-section, or half of a cross-section, if you will, of this cone. And this is essentially what's going on in that, like, half cross-section. We'd have a little right angle there, a little right angle there. So we know that this radius is 1, the height is 2, but we don't know what this is, and we don't know what this is. But we can set up a proportional relationship with this. We can say that 1 over 2 is equal to r over h. And that can actually help us out. We can now write r's in terms of h's or h's in terms of r's. And since it's wanting the rate at which the height of the water is changing, we should probably write r's in terms of h's. So we want to solve this for r. We can move some things around, and we can have h divided by 2 is equal to r after some algebra. And we can actually plug this into the original volume formula, and then we'd have less variables to work with. So let's go ahead and do that. If I substitute that in, we would have volume is equal to, we have 1/3 pi, so I'm going to do pi over 3. And then instead of r squared, we could have h divided by 2 squared h. We can clean that up a little bit. We can square a fraction by squaring the numerator and denominator separately. So that would give us h squared over 4, and then we can multiply everything straight across. So that would give us pi over 12 h cubed is equal to the volume. So the volume at any given height is defined in this scenario as pi over 12 times whatever that height is cubed, which helps us out. We go from an unknown quantity and an unknown rate. Oh, I messed up the rate here, but that's fine. An unknown quantity and unknown rate to we don't even need that information. Which is very useful. Let's go ahead and differentiate this. Oh, I might have to have my pen tool. So d dt of this would be dv dt is equal to, well, bring down the power 12 thirds, or 3 twelfths, my bad. That would be pi over 4 h squared dh dt. We know that the rate is constant for the change in volume, but we don't really know what it is. We don't know what the height currently is. So what we're going to do is we're just going to move everything that we can over so that we solve for this dh dt, because that is what it's wanting in the end. So we could have this turn into dv dt, and that divided by pi over 4 h squared is equal to dh dt. And if we had those values, if we could find those values, then we'd have like a concrete answer. But for now, that's all we really need. So that is setting up related rates, and it's a lot of work. It can be. And the problems can be a little bit weird, like this one, seemingly randomly having similar triangles. So the more of these that you do and the more you practice with this, the better off you'll get at noticing some of these nuances, some of these intricate and interesting relationships. So let's actually go through the full process now with two of them. We're going to be solving some related rates problems. We're going to go through the whole process here. I have two problems that we have enough information to be able to completely solve. So what I want you to do is I want you to copy them down, pause the video, and I want you to try your best to solve them, or at least get as far as you can. That way we have a starting point and a way to kind of check what you're doing against what I'm doing. It also gives us a start for any discussions that we might have. So hopefully with my little ramble, you have paused the video and you've actually copied these down for me. I'm going to move the second one out of the way for us. And here we go. So two airplanes are flying in the air at the same height. Airplane A is flying east at 250 miles per hour, and airplane B is flying north at 300 miles per hour. If they are both heading to the same airport located 30 miles east of airplane A and 40 miles north of airplane B, at what rate is the distance between the airplanes changing? So let's draw what's going on here.
We have two airplanes. I am going to do my best not to take forever drawing them. So we have two airplanes. There's one that is flying east, if I'm not mistaken. Yep, it's east. And this other one is coming from the south. It is going north. So I'm just going to do that. And they are both heading towards the same destination. Alright, so this is a very crude picture, but this is what we've got going on. And it is a 90-degree angle there because we are dealing with something that's traveling west to east and something that is traveling south to north. Those will intersect at a 90-degree angle. So that gives a clear idea of what we might be using here as our relationship. We currently know that this here is 30 miles. And we know that this is 40 miles.
If we use Pythagorean theorem, we would know that this would be 50 miles. It's also a 3, 4, 5 triangle, which is very, very nice. I'm going to call this big A, and I'm going to call this big B for purposes.
So we know that if we make our list of what we know, big A is equal to 30 miles. We know that dA dt is equal to airplane A is flying east at 250 miles per hour. And we know that big B is at 40 miles currently. and we know that its speed is 300 miles per hour. And we know in this case that we'll call it big C. Why not? Big C is equal to 50 miles. And we also know that we want to find the distance between the airplanes is changing. So we want to know the rate at which this is changing. So we want dc dt. That is what we want.
You'd also just put a question mark if you'd like. That is going to help us. Ooh, wrong thing. Nope. There we go. This is going to help us with setting up some of those relationships. So Pythagorean's theorem is going to be the overarching structure we're going to use. And if we go ahead and use our values, we know that a squared plus b squared is equal to c squared. All capitals for our cases here. Now, question I have, and that I'm going to answer myself, is kind of rhetorical. Why am I not just saying 30 squared plus 40 squared equals 50 squared? Because that is how I found this. I used Pythagorean theorem to find this. I found this myself. We found that ourselves. Why can't I just plug those in now? Well, it happens to be when we differentiate this. If we differentiate a constant, it would be 0, but we know that they're moving. So the derivatives aren't 0. These are not fixed. They're just at the snapshot in time, what are they? But we're modeling the relationship overall. So the derivative of each of these would be 2 big A dA dt plus 2 big B dB dt is equal to 2 big C dC dt. Now, if we want to be technically accurate, which I guess is the best kind of accurate, this distance, the speed this is going in on itself. It is decreasing the actual distance over time, so that would be negative. This is also decreasing the distance over time, so this speed is going to be negative. And we know that this is going to shrink, which also means that this is going to be negative. So in the end, it really doesn't matter, but semantics, they are negative numbers. So let's treat them as negative numbers. That way we don't mess anything up along the way. So the first thing I'm going to do before I plug anything in is you have a 2, you have a 2, and you have a 2. Let's divide everything by 2. So that gives us A dA dt plus B dB dt is equal to C dC dt. Let's plug in some values, shall we? A is 30. dA dt is negative 250 plus B is 40 and dB dt is negative 300, and that equals C, which we found to be 50. Remember, we found that wasn't given to us, times this dC dt, which is what we want. And if you notice, what we want is the only unknown thing we have left, so we can solve for it. So 30 times 250, well, 3 times 25 is 75, and then we have 2 zeros, that is negative, and then we have 40 times 300, 4 times 3 is 12, and that would have 1, 2, 3 zeros, negative, equals 50 dC dt. Now, when we subtract from a negative, it's the same thing as adding, so that would be 19500. If I did that correctly, I believe I have. I'm going to take my word for it anyway. 50 dC dt, and then we would divide by 50. So let me actually grab a calculator, because I'm good, but I'm not that good. Negative 19500 divided by 50. That would be negative 390 miles per hour is equal to dc dt. So that is the rate at which the distance between the airplanes is changing. It is getting smaller. That distance is decreasing by 390 miles per hour. All right. Hopefully we're feeling good about that one. Next up is another challenging one. So we have a vertical cylinder, and it's leaking water at a rate of 1 cubic foot per second. If the cylinder has a height of 10 feet and a radius of 1 foot, at what rate is the height of the water changing when the height is 6 feet? So, a cylinder is a prism, a special type of prism, and the volume of a prism is equal to the base area times the height. And with a cylinder, the base area is a circle, so volume is equal to pi r squared h. And let's draw what's going on. I think it's really important before we start listing anything off to actually draw the situation, because this one might get a little bit weird. So we're going to draw an oval-like thing. We're going to bring them down. Oh. And we're going to try to draw our best oval-like shape there. That works. Perfect. And that is filled with water. We don't know exactly what's going on there, but we have an idea, and it's, filled with water. All right, so what do we know about this cylinder? We know that the water is leaking at a rate of 1 cubic foot per second. So that would actually be dV dt is equal to negative, it's leaking, it's going down, 1 cubic foot per second. We know that the cylinder itself in its entirety is 10 feet tall. We know that the radius of the cylinder is 1 foot. At what rate is the height of the water changing when the height is 6 feet? So the height at the given second we're worried about is 6 feet. So what does that mean for us anyway, right? So, yikes, right? What's changing? I want you to think about what's changing over time in this shape. A cylinder is actually quite a nice shape if you think about it, because you can imagine it's just a bunch of congruent circles stacked on top of each other. What that means, in, a more basic way, is that the radius is not changing. The radius is a constant, which is really going to help us out when it comes to a derivative. R equals 1, and I'm going to put that it's constant, 1 foot. And it's constant at 1 foot. It's unchanging. The original height is 10 feet. The height at which we're worried about is 6 feet. So let's take the derivative of this and see what's going on. So the derivative of v equals pi r squared h, since the 1 is a constant and it's staying consistent, we can actually plug that in now. So v equals pi h. Then we can take the derivative. dv dt is equal to pi dH dt. With the information that we have, just to reiterate, we determined that the radius was constant throughout the cylinder. And that is really, really important because this relationship is very, very simplified. Like, there is no radius, there's not a lot of weirdness when it comes to this. If we substitute in dv dt, we have -1 equals pi dH dt, which means that dH dt is equal to -1 over pi, and that would be feet per second. And why does that necessarily make sense? Well, we know that it's losing 1 cubic foot per second. We know that the entire cylinder itself only has 10 pi cubic feet in volume, and if the volume is going down 1 foot per second, then that leaves us with a very direct and very almost simple relationship between the height and the volume, and that is why we have such a simple answer there. So it's a little anticlimactic. I thought I was doing it wrong with how anticlimactic it ended up being, but that is indeed the final answer. So please do not get discouraged when it comes to related rates. These problems can be a little weird, they can be a little wonky, but almost all of them are some sort of actual thing happening, whether it's water leaking out of something, a ladder falling down, airplanes going to hit each other in the sky, or what have you. Think about what they are doing in context, and if your answer actually makes sense in this context. And in this case, it does. The height should be decreasing, and the rate at which it's decreasing isn't absurdly weird. It makes sense in the context, really. It makes sense that this 50 is decreasing faster than the other two because it's got more distance that has to close in and be 0 at the same time. If the planes are going to collide with each other, which hopefully they don't, that would be awful, the distance between them would also be 0. So it does kind of make sense of the problem, and you just have to try to interpret and make sense of it. So again, here are the 5 steps. It's not important to memorize what they are. They're just good steps for any problem-solving venture. Drawing a picture, writing down what you know, making an equation, and then what makes it related to rates is really just differentiating that with respect to time. So implicit differentiation is going to be your friend here. And then substituent solving. So the last 2 is really what makes it related rates. Everything else is just word problems you've been doing for most of your mathematics career. So that was some related rates practice. We had objectives of setting up related rates and solving some problems using related rates, and I feel like we've accomplished those. If you'd like more practice, please, there are plenty of sources online. Keep practicing, keep asking questions, and ask your math teacher. If I'm your math teacher, awesome. If I'm not, ask your math teacher, and maybe that can spark some really interesting discussions between you and them. Anyway, I hope that you have a great day, and I'll see you in the next video.